Groovy. Then look to the course webpage to see that revision appear, and then also look to Canvas for places to upload homeworks for this week to also appear. So then the topic we're going to hit today is talking about continuity. And we've done lots and lots and lots of stuff for sequences of numbers. And I alluded to in that recorded lecture that, well, the limit laws for limits of functions are basically the same as limit laws for sequences. And while that's true, you can do one better than that. You can translate things about continuity, limits of functions, to statements about sequences. Then you can just say, well, I know lots and lots of stuff about sequences. Let's just translate things to sequences, prove something about sequences, and then translate that. And there's a proof technique. We will verify that such a proof technique is valid today. That's our goal. So maybe I should ask this too. I have 2 of these. Does anyone want one of these? Cool. So let's start with a pop quiz. Fill in the following definitions. Of course, if you look ahead in the notes, you knew this was pop quiz was coming, so it's not a very good pop quiz. But how many people look at the notes before the lecture?
No, sir.
Okay, I would have expected like at least a hand to go up. It would make lecture, I think, more pleasant if you already know what's going to happen. But let's do it.
On the bright side, this pop quiz was hook, line, and sinker.
For a sequence n and a number L, we say that that limit is equal to L if what happens? Give me the definition of the limit of a sequence. Give me the definition of a limit point or accumulation point of a set. Give me the definition of an isolated point for a set. Give me the definition of the limit of a function. Give me the definition of continuity of a function at a point P.
So is there a date next week that the midterm will be on?
Wednesday? I was going to make it back by a week even.
Okay. All right. Not be looking back in the notes for this.
No, I want this to be like an actual memory exercise. I'm not collecting them.
Okay.
And we will fill in these blanks in, a moment.
Ooh.
Cool. People feeling like they're ready to come together? So you want more time to write quickly before we start?
A little more time, possibly.
Okay, more time. All right, let's do it. What does it mean to say that the limit as n goes to infinity of a sub n is equal to L? Yes?
For all epsilon greater than 0, there exists a big N, so that if little n is greater than big N, the absolute value of a sub n minus L is less than epsilon.
Cool. All right, so the way to read that, for any small error bound, you can get a sub n to be within that error bound of L. Not for all n, but instead there's some threshold value so that once n is past that threshold value, you have this approximation. A point P is called a limit point of U if anyone remember? Cool, let's write it down. Well, maybe, yeah, let's write it down and then draw the picture. For every positive number delta, there exists a point x in U such that so what's the picture of this? Here's the real number line. Here's some point P. This says if you look in any little delta neighborhood, you can find stuff in U at that neighborhood. That's supposed to be an X in U written in orange. So you can keep taking that delta smaller. You'll find X's that are closer and closer to P. That definition seems reasonable to be called a limit point. There's stuff in X in the set U that limits to P. What does it mean to be an isolated point? Yeah.
I believe it's the opposite of that. So for all delta greater than 0, there exists an X in U such that 0 is 0 less than, or 0 greater than or equal to X minus P is greater than or equal to delta.
I like the fact that you said it's the opposite of that.
Yeah.
A point in U is an isolated point if it's not a limit point.
Yeah.
But then you failed to correctly negate this.
Okay.
So, for every delta bigger than 0 will become a...
Oh, there it exists.
Such that an X in U will become...
For all.
And maybe I'll mess around with negating that and like write down something maybe a little bit more useful. So if you negate that, that must mean either 0 is bigger than or equal to X minus P in absolute value, but that would just mean X is equal to P, right? Or X minus P in absolute value is bigger than delta. So either. So one option is X is equal to P, or absolute value of X minus P bigger than or equal to delta. And then pick your favorite other way of rephrasing that. Yeah. Oh, yeah, sorry. Yeah. Cool. And I guess another way you could phrase that, this is, I don't know, how about this? If absolute value of X minus P is less than delta, then X equals P. Does that mean the same thing as the line above? Yeah.
That first line, say X greater than P.
Equals. X is equal to P, or the difference is bigger than or equal to delta. For a set U and a function f defined on U, and a limit point P of U, a number L, and a number L, we say that the limit as x approaches P of f of x is equal to L if what happens?
This could be totally wrong. I kind of spitballed this one. I have for all. Oh,
Let's,
okay, my thing makes no sense at all, sorry.
so let's start with like the final thing and walk our way backwards. All right, there's the thing that, like the payoff at the end of the definition of the limit. F of x should get very close to 1. Should I be able to pull that off from absolutely every choice of epsilon?
Yes.
All right, okay, but that inequality doesn't happen for every choice of x. It only happens for x values that are pretty close to the point where you're taking the limit. So there exists a delta bigger than 0. That delta is like the threshold value. Once x is this close to p, you get the conclusion. Such that for all x in the domain U, if, and I'm intentionally leaving myself a space here, absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon. That one. Right. That seem reasonable? What am I missing though? What goes next blank that I set aside? Nice. Right, so the reason for that is the limit as x approaches p is equal to L should have nothing to do with the actual value of f at p. It's totally independent. So you need to find a way of not giving a shit what happens when x equals p. Putting that condition there is how you do that. Feeling pretty good? Great. So same thing, but definition of continuity. What does it mean to be continuous at a point p? Yeah.
I put the limit as x approaches p of f of x equals L.
X approaches p. F of x equals L. Nice. So I wouldn't call that the definition, but there is a theorem where we prove that that's equivalent. Right, it was this theorem. As long as you're looking at a point in the domain which is a limit point, these things are equivalent. But is every point in the domain always a limit point of that domain? No, your domain could be like the integrals. In which case, like everything is isolated. We proved that any function is automatically continuous at an isolated point of the domain. So kind of that just means if you're at an isolated point, why are you talking about continuity anyway? So this is, in some sense, close enough to being an if and only if. But it's not the definition. What's the definition of continuity? I guess you could figure it out by thinking about that.
For all epsilon greater than 0, yeah. I mean, if we just take straight up the limit, then we just go with, like, if there exists something in, for, I guess, some double on, then, okay, so it'd be like a flat delta thing. So x in u, and then we have 0 between x minus p, and then less than delta. So that we have, f of x minus L less than epsilon.
So notice that's almost exactly the same as the line above. And in fact, what you said was the same as the line above. Oh, and that's not L. There should be an F of P.
Oh.
Right, the limit being equal to the function value of a bunch of mean continuity. Notice I left out the 0 as less than. And that's because continuity should care what happens when you plug in E. But notice you'll get the same definition even if you put the 0 as less than there. Because what would be the other case? Like you would be going at the case that x is equal to p. If x is equal to p, then f of x minus f of p less than epsilon. Yeah, because they're equal. Nice. All right, so there's the setup and recollection. Oh no, one more piece of setup and recollection. So here are these two theorems. A function for a subset U, a function f defined on U, and a point p in U. Theorem 7.1.5 says that if p is also a limit point of U, then this function is continuous at this point p if and only if the limit statement. so exactly what you said, and it's close enough to being true because the only exception is isolated points. If P is an isolated point of U, then the function is automatically continuous at P. It doesn't matter what the function is. Every function is continuous at isolated points. Yeah?
Scrolling up to the third line again of the definition, I just want to make sure that we have x equals P, or is the absolute value of x minus P?
There?
One up. There, in the bracket there. That is absolute value of x minus P?
Yes. Anyway, if you just remember, it's not a limit point.
Yeah.
That's good enough. In fact, that is the definition. The other thing is just what does logic tell you it has to be. Neato. So I promised you that we would translate between the setting of functions and the setting of of sequences. And the following three theorems are the three theorems that let us do that. 7.2.1, the sequential reformulation of what it means to be a limit point. So here's a different definition of what it means to be a limit point. Let U be a subset of R, P be a point in U. Then P is a limit point of the set U if and only if there is a sequence of things that are in U different from P which converge to P. And that hopefully makes sense. Right, what does it mean to be a limit point? It means you can keep on finding stuff close to it. Well, that means you can find a sequence while the stuff is close to it. Sequential continuity. Let U be a subset of R. F from U to R be a function. P be a point in U. Then F is continuous at P if and only for every sequence of inputs which get close to P. It follows that F at those inputs gets close to F of P. So that says that if you want to prove something about continuity of functions, just translate to sequences, prove things about sequences, then translate back to continuity. There's the strategy that this unlocks. And the same thing is true for limits of functions. Let U be a subset of R, F from U to R be a function, P be a limit point of U, L be a number. Then this limit is true if and only for every sequence of elements of X minus P. So notice here, there's a difference between those two formulations. But notice that makes sense that there would be that difference. Continuity cares what happens when X is equal to P. Limits don't. So you shouldn't consider any sequences which are equal to P. Such that this is n. Otherwise, it's like the same statement. That seem pretty reasonable? Yeah.
And is there a discontinuity at P because you're converging to it, so you have to have an infinite iteration of whatever your sequences to get there? Is that why there's you don't want to go to P?
You do want to go to P, you just never want to be at
P. Is that actually P at infinity? That would be a problem?
Kind of.
Okay.
Right, so the reasoning is the same as the reason for this 0 is less than.
Okay.
The limit doesn't care what happens when you plug in X equals P. So you don't want to look at sequences that see what happens when X equals P. So leaving out this point P right here, so don't consider sequences which see X equals P. I don't want sequences that ever know what happens when X is equal to P. Because the limit doesn't care what happens when X is equal to P. Nice. So there are some theorems. What I'd like to do is first do an application of these theorems, then prove some of these theorems, and then, well, that'll be all the time we have, really. So let's start with applications. So here's the application I would like to do. So here's a theorem that was stated last time. Limit laws for limits of functions. I told you that, all of the proofs on the one hand were like the same as the proofs for sequences. But you can also prove them now using the fact that you know stuff about sequences. So let's try to prove these. And maybe we'll start by just restating them. If you have a constant function, what's the limit of that constant function?
C.
If f of x is always equal to x, then what's the limit as x approaches p of that function?
C.
Nice. As x gets close to p, x gets close to p. Sums of limits, what goes in this blank?
F x equals p of x? Or rather, f of p equals p of p?
Not continuous.
Uh,
L plus n.
oh.
And subtraction?
L minus L?
Multiplication?
L times it?
Division, where you make sure that you never accidentally divide by 0?
L over n.
And I will only give the proof for the claim about division. Maybe we'll talk about how you would adapt this to do any of the other things. So here is the thing that we want to claim. According to, so I guess we should get the setup. Assume U is a subset of R, P is a limit point of view, F and G are functions from U to R. There's no assumption that they're continuous. Assume that the limit as x approaches p of f of x is equal to L, limit of g of x is m. That g of x is not equal to 0 ever. That the limit of g of x is not equal to 0. So that's just all of the assumptions. And there were a lot of them. Our proof will pass through theorem 7.2.3, and maybe I'll even do this. I'll put that theorem on the board so that we can reference it. It's on the previous page now. So theorem 7.2.3 says the limit of f of x as x approaches p is L if and only if for every sequence x sub n of elements of U different from p, if x sub n converges to p, then f of x sub n converges to L. So instead of trying to prove a statement about the limit here, I'll prove something about any sequence of limits. So let's do that. So we will consider any sequence of elements of U minus p. We will assume that x sub n converges to p. We need to prove maybe I'll just insert a quick want to show. We apparently then want to show the limit of f of x sub n divided by g of x sub n equals L over m. That makes sense why that would complete the proof? And then I would have this. I could go through. Alright, so that orange thing is the thing I want to show. But I certainly know the limit of f of x and the limit of g of x. So according to theorem 7.2.3, what can you tell me about the limit of f of x sub n? That's the thing we called L. And we can do the same thing for G, right? All right. So now I know the limit of f of x sub n. I know the limit of g of x sub n. I would like to compute the limit of f of x sub n divided by g of x sub n. Do I have limit laws that apply for limits of sequences? What's the limit of that fraction?
The limit of each fraction part?
Yeah. All right, and what is the thing on top of that fraction?
L.
What's the thing on bottom? All right. So what did we do? We considered any sequence of elements of U different from P. We assumed that those inputs converge to P. We proved that F divided by G, when you plug in X sub n, converges to L over M. This is an if and only if, so we can go the other way and make a conclusion here.
Thus, we see for any sequence X sub n of elements of U minus P, such as X sub n converges to P, it follows that this limits to L divided by M. By theorem 7.2.3, we conclude that the limit as X approaches P of f of X over G of X equals L over M. This completes the proof.
That seemed pretty okay? Yeah. And maybe there are some things to notice here that are nice. There were no epsilons and deltas. In fact, the proof, we just used things that we already knew. We said I'm going to translate to sequences. I'm not going to worry about where the limit was for sequences came from. I'm just going to say I know that they're true, so I can use them. Now we'll translate that. How'd that feel? That seems like a useful theorem? Yeah.
So it's useful to be able to translate things to sequences and then prove things about sequences. And now let's start in on the proofs of these three theorems. We'll start with the one that seems easiest for us. We'll do 7.2.1, which maybe I'll recall right here. Theorem 7.2.1 says P is a limit point of U if and only if there exists a sequence X sub n of elements of U different from P such that X sub n converges to P.
So let's just analyze this statement and decide how the proof should go. It's an if and only if claim. So I guess I need to do two proofs. One of if, the other of only if. In the proof of if this, then this, I get to compute the limit point that I need to come up with a sequence. So let's start by doing that. Let's assume that P is a limit point of U.
Recall what that means? What's the definition of a limit point?
By flipping back to the previous page if necessary, or by memory ideally.
For all delta greater than 0, there exists an X to U such that 0 is less than the absolute value of X minus P, which is less than
Cool. I need to find a sequence of elements of U minus P such that X sub n converges to P.
And let's try to talk about how to do this. And one would be an idea that we've used with some success in previous things, like talking about suprema of sets in terms of limits of sequences. I have this statement for absolutely every constant number delta. So can I take a sequence form of deltas and get a sequence form of x's? Yeah. And here what happens when delta gets small, so I want a sequence of deltas to get small. What's your favorite sequence of positive numbers that converges to 0?
Sorry, can you do that?
What is your favorite sequence of positive numbers that converges to 0?
1 over n?
Right. Yeah, that. Of course. If you are sufficiently computer sciencey minded, maybe you would say like 1 over 2 to the n. But 1 over n does the trick, and it's maybe the simplest example. It seemed like there was a question over here.
Ooh, yeah, that's kind of illegible. Of, and this is like an abbreviation I use a lot for elements. And elements is a really long one. Else.
Otherwise, the thing is sensible.
set minus. So of u, take away p. Yeah, so maybe I'll try to follow a convention. For set minus, who would prefer a straight up dash as opposed to a slashy thing? Dash? Slashy thing? Alright, well, whatever's in the notes, what's in the notes. I can't change that, but I'll try to start using a minus sign for minus instead of slash. Set minus. Cool. So let's try to do it. Let's proceed. So we'll find a sequence worth of deltas. That's at delta n be 1 over n. I can use the fact that p is a limit point to do something. There exists some xn which depends on the choice of delta, which depends on the choice of n. So it really is an x sub n, such that 0. Yes. Is less than
and maybe we'll just start with this. We need the set of elements to be elements of u set minus p. So I need them to be elements of u that are not equal to p. Do I already have that they're elements of u?
Yes.
Do I already have that each xn is not equal to p? Yeah, basically. Like the 0 is less than does that. Maybe I'll add that in these lines.
since 0 is less than absolute value of x sub n minus p, x sub n is not equal to p. So x sub n is in u minus singleton p.
All right. We have our sequence now. What do I need to show about this sequence?
That it converges to P.
That it converges to p.
And like there's a straight up like epsilon n argument here. I guess we also need, well, we already have that. We already have a sequence of elements of u minus p.
So if you want to see a sequence which satisfied this inequality and wanted to show that x sub n converges to p, what strategy would you want to follow?
So you spin epsilon group?
Great, let's do that. So,
All right, so let's prove. I think I want to splash that out too.
so how do you prove a limiting claim? You need to consider any epsilon bigger than 0. You come up with a choice of big N. We'll consider any little n bigger than big N. Then, absolute value of x sub n minus p
Is strictly less than delta n.
And what is delta n equal to?
1 over n.
1 over n.
All right, I eventually need that to be less than big N. 1 over n, that like gets smaller as n gets bigger. So since little n is bigger than big N,
This is less than 1 over big N.
Yeah.
is there a trace of big N that you could use to have that be equal to epsilon?
That,
Yeah, I mean, when in doubt, you can solve this equation, right? If that means you go to the merger, you go to the merger. Right, couldn't solve that. You just need to solve that. Yeah, it's 1 over epsilon.
Thus, we've proven that the sequence converges to P. Now let's see. We already have x sub n is in the set u set minus P already, so I'll slash that out. Maybe I'll write a concluding sentence. Thus, if P p is a limit point of u, then there exists a sequence x sub n of elements of u minus singleton p, such that x sub n converges to p.
All right, that seems pretty okay. Let's go the other direction.
So let's assume, or maybe I should pause for a moment. Yeah.
Are we filling out that last line there?
No, what was going to go in that last space was like an argument that x sub n is not equal to p.
Okay.
But that happened up here instead.
Okay.
Feel pretty okay? Yeah.
I guess I just missed it. What's the significance of the sequence, or the significance of the sequence going over n? Like, why do we do go over n with the sequence?
So let's see what we needed delta n to do here. So I needed delta n for n big enough to be less than epsilon. So I guess that means I needed delta n to converge to 0. What's your favorite sequence that converges to 0? 1 over n. So that's all we needed delta n to be 1 over n to achieve. You could have taken anything else that was always positive and converged to 0 and get approved. You could even just been more vague, saying, let delta n be a sequence of positive numbers that converges to 0. Groovy. So let's go the other way. Let's assume there is such a sequence. Let's assume that xn is a sequence which satisfies that for all n in n, x sub n is in u minus p, and such that x sub n converges to p. We need to show p is a limit point. What does it mean to be a limit point?
For all delta greater than 0, there exists an x in big N, in big U, sorry, such that 0 is less than the absolute value of x minus p, which is less than delta.
All right, so there's the thing we need to prove. So I guess if we want to do this, we start by considering any positive number delta. Then I need to come up with an element of the set big U, and that thing needs to satisfy the set quality. And we can use the convergence of the sequence to pull that off. So let's do that. Let's fix this positive number delta. Delta is positive, and x sub n converges to p. What does that let me conclude? Definition of the limit.
The absolute value of the difference is less than that one?
Yeah. Right now the positive number I'm thinking about is called delta.
Oh,
And that's not true for every choice of big N, right? But you left out some odds.
okay. And could that be like the sum of little n greater than big N right now?
And for what choice of big N?
Where that's the big N we just solved for?
No, we're in a different step of the proof, so this is unrelated to that.
Okay.
Yeah, I don't know what like I don't have a sequence called delta n at all.
Okay.
So there's just the definition of x sub n converges to p, right? For every positive number I could do that. Delta is a positive number, so I can do that for this choice of delta.
Yeah.
Does this give me a lot of the things I want? Do I know that x sub n is an element of the set big U?
Yes.
I wanted to get absolute value of x minus p is less than delta. I have absolute value of x sub n minus p is less than delta. It looks like all I need is the 0 is less than here. How can we get that 0 is less than to appear? Yes, awesome. So that will do it. And in fact, that's just an assumption, isn't it? So let's consider any little n bigger than big N. Then what do I have right now? I have x sub n as an element of the set big U. And I have absolute value of x sub n minus p is less than delta.
to get 0 is less than, well, what do I need? I just need to absorb that
as x sub n is in u minus p. X sub n is not equal to p. So 0 is less than the absolute value of x sub n minus p.
Cool. So does this x sub n do all of the things that I need it to?
Yeah.
Yeah, I think so.
Let's just summarize. Thus, for every choice of delta bigger than 0, because we started by considering any delta, we have constructed an element, which we called x sub n, of u set minus p, such that 0 is less than absolute value of x sub n minus p is less than delta.
That's exactly the definition of a limit point. This thing is a limit point. That's exactly as we planned. Does that argument make sense?
Cool. So let's start in on this next proof. I think I'm going to run out of time pretty quick. But we can make progress. I think we should be able to get half of it done. So let's prove theorem 7.2.2. And for convenience, there's the two things that we need to show are equivalent. A function is continuous at a point p if and only if for every sequence of elements of u, if x sub n converges to p, then f of x sub n converges to f of p. Cool. So let's do it. All right, and I guess there's the assumption. Let u be a subset of R, let f be a function, let p be a point in u. So let's do this. Let's suppose that this function is continuous at p. Let's consider any sequence of elements of u such that x sub n converges to p. Right? We want to show something is true for every sequence of elements of u. We want to show that if-then. How do you show an if-then? You assume the if-then. Yeah?
Just want to make sure this is just all straight in my head. So then those are subsequences of u, correct?
They're not subsequences of u because u isn't a sequence.
Oh, because u is a set.
But u is a set. They're sequences of elements.
Out of them.
Yeah.
Okay.
So you could take a subsequence of that xn, and a sequence of elements of a set seems spiritually similar to a subsequence.
Yeah.
But it's not, the big thing is in a sequence, so it's not technically a subsequence.
Okay. All right.
Nice. So we need to show that f of x sub n converges to f of p. Well, how do you show a thing converges to a thing? You need to show that for every epsilon bigger than 0, there exists a big N such that blah, 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 blah. Let's try to do that. We'll consider any epsilon bigger than 0. And here's how I'll try to have the logic broken up.
So eventually I want I need that to get small. The function's continuous though, right? So as long as this input is close to that input, then I think.
Yeah.
That's what continuity means. Oh wait, do I know that the sequence x of n gets close to p?
Yes.
Nice. And here is a fluid. We'll just unravel this. Yeah.
What, I forget this, we mentioned this before, we can go from sequences back to functions. What was the total of upstairs again?
It's the theorem that we're proving right now.
Oh, this one.
Yeah. They were these three theorems. This one says instead of thinking about limit points, you can think about sequences. This one says instead of thinking about continuity of functions, you can think about sequences. This one says instead of thinking about limits of functions, you can think about sequences.
Oh.
But you can't assume that result if you're trying to prove that result.
Yeah.
So we have to think about sequences now because we're proving something about sequences.
Okay.
So let's do this. So the first thing in this argument was we use continuity of f to come up with a delta.
Since f is continuous at p, there exists a delta bigger than 0 such that for all x in u, if this then
And notice I have num on that line. I will refer to it later on as 7.1. The next thing I did is I used the fact that this delta is positive and this convergence result to say there exists a big N such that this arrow happens.
Since delta is bigger than 0 and x of n converges to b, there exists some big N such that for little n bigger than big N, that happens.
All right, so now back to the big picture. I wanted to show the convergence of a sequence. So I started by considering any epsilon bigger than 0. Have I now come up with a choice of big N? Yeah, I mean, it's not explicit, but there was no hope of it being explicit.
Let's see if this big N works. So let's consider any little n greater than that big N. And now we'll just trace back through this. So since little n is bigger than big N, what can I conclude using 7.2?
That the absolute value of x of n minus p is less than delta.
Nice. So what can I conclude using 7.1?
That the absolute value of fx minus fp is less than f4?
Yes, except there should be a sub n somewhere, right?
Yes.
But I know
Oh, fx sub n.
I know that x sub n satisfies this inequality. I know that whenever anything satisfies this inequality, then that inequality happens. Oh, hey, is that exactly what I needed to conclude that f of x sub n converges to f of b?
Yes.
Groovy. So, with 1 minute remaining, that's not enough time to do the opposite direction of the proof, but maybe I'll tell you about how the proof will go, the global structure of the logic. So what would I need to prove? I would need to prove if something about absolutely every sequence, then the function is continuous. But that's too hard, like a hypothesis to use. So instead, maybe I'll try to prove the contraposition. So instead I'll assume not f is continuous, and then try to prove not this. So I'll assume the function is not continuous. Now I need to essentially come up with a sequence worth of inputs that sees the failure of discontinuity.
It sounds kind of like a proof that covers it.
Yes, and it is.
Okay.
Because you assume something's not continuous. You want to show not a universal statement. You show a universal statement is false by finding a counterexample.
Oh, excellent.
Cool. And we'll do that next time. So, as a reminder, the schedule online will be changed by, let's say, popular demand. There were more votes for than against. There will not be an exam on Wednesday. The exam will be pushed back by precisely 1 week, and will cover the same content.
Cool.
I'll see you on Wednesday.
Yes, because we have class on Wednesday, right?
Yeah, and before.
Okay, awesome. Let's see you, Professor. Ciao.